as we go along. All right, and so today's talk is given by Hiroshi. Hiroshi has been working on all sorts of interesting topics of, how should I put it, numerical analysis for realistic quantum materials, maybe. That's a good way of putting it. And one of the things he's done is finding compact representations of bases for Green's function in imaginary time, in frequency, for analytic continuation and everything like that. So Hiroshi, go ahead.
Yeah, thank you for the introduction. So I have probably 1 hour. So I want to tell you something about how to use our new representation. It's not new anymore, but well, new representation and sparse sampling techniques for imaginary time propagators in ab initio calculations and many-body calculation. And I want to focus on some practical points of this technology. Okay. Oh, something wrong. I'm going to talk about 3 things. One is the compact representation. So the basis size grows only logarithmically with beta at low temperature. It's quite nice. And in the second part, I will talk about our sparse sampling techniques for solving diagrammatic equation at the 1 particle level. And in the last part, I will give you a more detailed explanation on numerical details, and we provide some numerical demonstration. And we explain our libraries and some, well, time model calculation. Okay, that's it. So let me start right. I want to do some introduction. So as you know, our Matsubara Green's function has been widely used. This is a response function of your system, of course, but this is a building block of various computational many-body theories like GW and DMFT and other embedding theories, and also some QMC method. And we have to deal with numerically very efficiently in our calculations. And Green's function, our Matsubara Green's function is defined on Matsubara frequencies on the imaginary axis, and GR is related to the physical spectral function, which is defined on the real axis, and through this integral equation. And this is the well-known Riemann representation. And interesting property is, even if we have some sharp peaks in the spectral function at high frequency, and if we go from spectral function to real Matsubara frequencies, those features or peaks are smeared out. So the Green's function is essentially a smooth function. So this makes it suitable for numerical simulation, because in principle, we need, well, rest basis function to expand the frequency dependence. But this also makes it difficult to reconstruct the spectral function from the numerical data. This is a infamously difficult problem, and many people have been working on. But I will focus on the numerical simulation in imaginary time. Okay, this is how you solve diagrammatic equations, and this is the simplest case, second-order perturbation theory for the Hubbard model. And there, essentially, you have to do 2 things. One is you have to solve diagrammatic equations, such as Dyson equation, or you have to evaluate this diagram, and in frequency or in imaginary time. So some equation can be evaluated efficiently in frequency, and some other things are evaluated in efficiently in time. So as a result, you have to transform numerical data between the 2 domains efficiently and also in a numerically suitable way. So that's the two things you have to do in ab initio calculation and many diagrammatic calculation. So first, I'll talk about how to store numerical data on your Matsubara-Green's function. The simplest approach, of course, using a uniform dense mesh in frequency. For given bandwidth or largest energy scale of your system, one particle energy scale, so you may introduce some cutoff in frequency, and you store all data below this cutoff, all Matsubara frequency points. And trivially, the number of frequencies to be stored scales like this: beta times energy bandwidth. And because this decay is in a parallel, you can reduce the truncation error only algebraically with increasing the cutoff for basis size. So this approach is simple, but in many cases is not accurate enough, especially if you want to do ab initio calculation at low temperatures. That's a problem. And of course, we could use our uniform dense mesh in imaginary time, and we end up the same scaling or the same problem, because you have to have some grid points near tycho 0 and beta and at low temperature. So this approach could be improved by using some uniform mesh or some cubic spline in frequency, but I'm going to talk about different approaches using some orthogonal representation. And there are several, sorry?
Sorry, yeah, on the last slide, you had Kononenko from like 2016 or whatever. This stuff is actually much older. So I think in Wei Ku's PhD thesis, this probably of the 90s or so, that's the first time that this power mesh was actually mentioned and then used for GW calculations.
Okay.
So this stuff is much older than sort of our codes here.
Yeah.
But go on.
Let me, fix it fix the slide later. Yes. So there are several other approaches, polynomial basis. So the essential idea is the Green's function G of tau is a smooth function between tau equals 0 and beta. So you can expand it using some complete orthogonal polynomials like Legendre or Chebyshev. And the advantage is that expansion convention decay exponentially down to some numerical noise level. And this means that you can improve the accuracy or reduce a truncation error exponentially with increasing the basis size L. And another interesting property is that, so at low temperature, this polynomial basis size is much smaller than the dense mesh, and the power is much smaller. And this is quite nice. So the problem is why we need better approaches or improved approach, because they are already looks quite nice. So this is why we need new technologies for Green's function, representing Green's functions. So sometimes we have to deal with low temperature physics and spin racket or some low temperature magnetism and low TC materials. At the same time, you have to deal with, in ab initio calculation, you have to deal with screening bands in solids or core states in molecules. And the ratio of the two energy scale is huge, and it's could be larger than 10,000. And at the same time, it depends on your system. So But at the same time, you need high accuracy, especially if you want to compute the spectral function by numerical analytic continuation. So the number doesn't have much meaning, but you may need a lot of significant digits in the input because analytic continuation is, well, ill-conditioned. So if you want to get right chemical accuracy in the ground state energy, you also need, well, this significant digit, well, could be more. And so that's why we need new technologies. So in that region, with 8 significant digits and large beta W, so you could need more than 1,000 coefficient even with Legendre and Chebyshev basis. So we definitely need a smaller basis size and, well, efficient way of solving the diametric equation. So this could be done by using our new technologies. Okay, so today I don't have much time to introduce these applications, but our new technology has been used in different contexts like GW and Flex, and this also has been extended to two particle sinks. And if you are interested in a particular topic, just please have a look at the paper or just ask me. Okay. So now the introduction is done. So I'm going to talk about the first thing, the intermediate representation. In this representation, the basis size grows only logarithmically, almost optimal with beta. Okay. Well, this is a Riemann representation for fermium in imaginary time, and this is a kernel in time. And we call this logistic kernel. And here we also introduce our UV cutoff, omega max. So a spectral function must be 0 outside this region or this interval. So because this kernel is smooth function and also integrable, so we can expand it by using SVE, singular value expansion. And so we get singular values and two sets of singular functions, and they are orthonormal, and we call them R basis functions. And here is singular values computed for different values beta. Sorry, I need to move this one. And omega max is taken to be 1, and from beta equal 110,000. And singular values decay are exponentially, and there's no degeneracy, and the scaled singular values are determined by the dimensionless parameter lambda, which is also important in this talk. It's essentially beta times omega max. So interestingly, if we increase lambda or beta by 100 from here to here, the number of spaces singular values grows only logarithmically with increasing beta. So the size is adjustable. So this is quite nice. And let me, so before discussing expansion coefficient or the compactness of the representation, I want to show you singular functions because it's quite interesting. And singular function, we call them, which we call R basis functions, looks like it is. So this is for tau and omega. And as you can see that UL and VL have L roots like other orthogonal polynomials. And this can be proven. And U and V are unique up to sign. And we usually take UL beta positive, like other polynomial basis. And another interesting property is this converges to Rojano basis function at high temperature limit. And this can be easily shown. And this means that these basis functions are a natural extension of the Rojano basis to finite temperature or lower temperature. Okay, but unfortunately, there's no known analytic form of these wave functions, so you have to do some numerical simulation. But it's provided by our libraries. So now let us discuss our compactness of this basis. So from lemma representation, we expand our G of tau and VL rho omega in U and V. So you end up this relation. And expansion coefficient GL are related to rho L and through this single value. And as long as rho L stay constant at large L, thanks to this SL, so GL decay as fast as single values, and single values decays exponentially, and system independent. That's the point. And let me emphasize that this relation is valid only if omega max is larger than bandwidth. So we can also expand the Green's function in frequency using our basis function in imaginary frequency And the remaining part is also decays like singular values. So let me introduce some example, very simple example. We consider two ports and our particle hole symmetric, and rho L can be computed like this by, well, evaluating this integral. And actually rho L do not decay at all. But thanks to the singular value, GL they'll decay exponentially. I think this is a worst case for our basis because usually data function at high frequency, well, cannot be expanded compactly in the R basis. But as long as we are interested in GL rather than rho L, so GL decays as fast as the singular value. So you can have some guarantee that the expansion coefficient for G are converged. Okay, now let me discuss what happens if we choose unphysical omega max. So omega max should be larger than W by definition. But we can also say, okay, for given exact Green's function, we construct some basis for our unphysical omega max, and we can expand it, and we can get some expanded coefficient. This can be done, and this is the result. In that case, the singular value decays super fast due to the small omega max, but GL decay slower than the singular value. This is because this nice relation is no more valid because omega max is smaller than W. So this is an indication of something went wrong in your expansion. So, and omega max equal 1 is optimal, but of course it's too tight because usually you don't know the bandwidth exactly. But a good point is the basis size grows only logarithmically with respect to omega max. So even if you take 10 times larger or omega max, your basis size is twice larger only. So my recommendation is please monitor decay of GL and SL always, and set omega max to a sufficiently large value, like 10 times expected bandwidth to be on the safe side. And don't try to optimize it. So the consequence is table. Okay, so I'll give you more examples how it fails, but let me focus on the basis again. So I've been talking about the fermionic basis, but we can use the same base function essentially for the bosonic correlation function. This can be shown that by using this equation. So this is a bosonic kernel, but after some manipulation, we again get the logistic kernel and with some regularized spectral function. And in the original R basis paper, we used different representation, but it turned out this definition has been widely used in lattice QCD community, and they also use this kernel for analytic continuation, and it is also proposed that we can use this kernel to construct R basis for bosonic correlation function. So we are now switching to this definition because of its simplicity. So we can use the same base function for fermion and bosons, but just technical detail. So now section 1 is done. So I'll give you some explanation on how to solve the diagrammatic equation by using sparse sampling. So if we use the dense mesh to solve the Dyson equation and to get GL, expansion coefficient of Green's function, you have to do like this. Well, there could be better way, but this is a naive approach. So you solve the Dyson equation at each frequency point, and after computing this Dyson equation on many frequencies, you evaluate this summation to get GL. But this, do we really need frequency dependence to determine GL? Because GL is right up to 100 or 30. So we need only a few GL to represent frequency dependence of GI nu. So why do we have to compute GI nu on, I don't know, 1 million or 1,000 frequencies? So our approach is simple. So somehow I will explain the procedure in the next slide, but we somehow choose good sampling frequencies. And the number of sampling frequency is slightly larger than the basis size. And we solve the Dyson equation on the sampling points. And then we transform to GL by some fitting scheme. And I don't want to call this fitting because it's quite stable, but essentially this is least squares fitting. And the choice of sampling point is not unique. There could be different ways of finding good sampling points. But our choice, our heuristic choice, it works quite well. And this is our choice. So we use the fact that our IR bases have properties similar to orthogonal polynomials. So they have L roots. So we fix the basis size L, and we look at the largest order basis function UL minus 1 tau. And you found L roots or L extremer. So we take these points as sampling times. Because lower order basis functions have less roots. And actually, these sampling points can capture all sign changes of all basis functions or all lower order basis functions. So we have a similar, we also found similar sign structures in the basis functions in Matsubara frequency space. And we take a streamer of imaginary or real part of basis function in imaginary frequency. And we sometimes add a few additional points for stabilization, but essentially these sampling points are enough. And there is another proposal or improved way of choosing sampling points. And this may be interesting point, how to improve the accuracy of sampling points. But anyway, for given some sampling points, so we can do our efficient transformation. But of course, the numerical stability of this transformation from sampling times to GL error basis is totally determined by the condition number of this fitting matrix F. F is a matrix consisting of the value of basis function on sampling times. And we have a similar structure between sampling frequencies and error basis. But as long as this fitting is stable, so we can do our efficient transformation between sampling times and sampling frequencies and sampling times. And as we will show you later, so we lose only a few digits in this transformation. Okay. And the numerical stability of this linear transformation is determined by the condition number of the fitting matrix F. And the condition number is a simple concept, and this is a ratio of the largest and smallest singular values of some fitting matrix. And if the condition number is 1, so you don't lose a significant digit, roughly speaking. And if it's, well, 100, you may lose 2 digits. So, but for our choice and of sparse sampling, so the condition number is so small, so you typically lose 1 or 3 significant digits, and it's not so bad. Actually, it's quite good. And actually, if we use randomly sampling times or sampling frequencies for our fitting problem or for sparse sampling techniques, the condition number actually diverges. So the choice of sampling times and frequency is critical for numerical stability. And once we have a nice rare condition fitting matrix, we can do fitting in a stable way using different approaches. But to be on the safe side, we use this scheme for fitting. So we first compute SPD of the fitting matrix. And so we evaluate the pseudo-inverse matrix and apply this to the Green's function on the sampling times or sampling frequency from the left. But to be on the safe side, we usually apply these 3 matrices one by one for improved numerical stability. And if F is in condition, this is not the case in your case, but if L is ill condition, this approach is much more stable. So that's why I'm using this in our implementation. This could be changed in future, but for now, we are using this one. So if you want to have h significant digit in your result, like Green's function or ground state energy. We typically add 2 digits to determine the cutoff value for single value. So, but my choice is use as many as basis function because it's not, well, I mean, the basis size is anyways so small. Here is, so I want to, well, demonstrate how accurate this transformation is. This is we consider a semicircular Denson state, and we try to transform numerical data on sampling times and sampling frequencies to IR basis. Here is a comparison between exact one and the reconstructed ones. So they match almost perfectly. And we have almost 14 significant digits. This is consistent with the small condition number and the small, well, cutoff value for senior values. Okay, now I briefly sketch how we do sparse sampling in practice. So in the third part, I will give you more numerical details. Now, actually, we have our basis library for generating sparse sampling points and evaluating our basis function. Actually, this library contains pre-computed basis functions for selected value of lambda. But recently, we have developed a new Python library, mostly developed by Marcus. And this Python library allows us to compute basis function for arbitrary value lambda on the fly within a few seconds or 10 or 20 seconds for even for lambda equal 10 to 7 spar. And in double arithmetic. So you have essentially full double precision for basis function. And this also contains all what you need for your practical calculation, like stable fitting, which I explained before, evaluation, and other, well, utility functions. And we can directly use this Python library for your calculation, or you can just use it for as a reference code to implement your code in C++ or in other languages. And our new Python, and we also have a Julia library. It's, well, it's still active development, but it implements almost all the functionalities of a Python library. And we have our Fortran interfaces, and we have a nice set of our tutorials on GWFlex. Oh, this is how about you, but and this explain how to use bosonic basis functions and flex and TPSC and analytic conjugation and more and more. I hope many people are going to join this project. So still we are collecting tutorials, but so this is some example Python code. So if you want to construct basis for fermium beta equal 10, omega max equal 1, so you need only one line. And then after that, you can do whatever you want. You can evaluate basis functions, or you can construct fitting object or transformation object. And internally, we use dimensionless representation. Because in the original representation, we have two parameters, beta and omega max. This is not so convenient. So we transform tau and omega to x and y. New dimensionless parameters are variables, And then we are left with only one single parameter, lambda, which appeared many times in this talk. And we can do SVE in these spaces. And once we compute basis function in this representation, we can transform back them to the original basis function. This is convenient if you want to store pre-computed IR basis function and singular values in a text file or embedded into some source file. And actually, our Fortran interfaces allow us to generate a source file containing tabulated IR basis functions. So no computation on the fly. So finally, I show you some show you how we solve the second order perturbation theory. And well, second order perturbation theory I explained before. So we starting from the Green's function. So we go to our real time space and imaginary time using FFT and sparse sampling, and the order can be extended. And after evaluating the safe energy, you come back to the original frequency decay space by FFT and sparse sampling. So my focus is on to show how it fails. And this is a right starting point. No interacting with function. And you have data on the sampling points, frequencies, and you convert it to a time domain. So you have many sampling times here, 0 and beta. And you can evaluate the safe energy on the same sampling times. And we come back to the frequency space. So we can monitor the expansion coefficient of the safe energy in the middle to make sure that the expansion coefficient decays nicely. I mean, at least as fast as the singular values. And of course, in doped case, you have to subtract the Hartree term because Hartree term cannot be expanded in the R basis compactly. Okay. So now I use, in the previous slide, I used 10 omega max 100. That is much larger than the non-interacting bandwidth 8. That should be safe because C equal just 2. But decreasing the cutoff, you see some signature of failure already at 10. It's marginal. You see some, right? The expansion coefficient shows some plateau. And it becomes worse if we actually go below some cutoff like this. So that's why we have to monitor the singular expansion coefficient carefully. So the tutorials contains more and more samples like GF2 and GW flex, and also area-Schell equation for Holstein, Hubbard model, Lichtenstein formula, and numerical analytic continuation, and any contribution to the library and tutorial will be welcome. It's nice to have a set of example codes to see how it works, how to code, and also we need some example to show how it failed probably. And this project has been supported by many things. Of course, funding sources are important, but I've been collaborating with many people. And I cannot show all names because I've been collaborating with many people, but I especially thank these people for long-term collaboration. So if you want to know more about new technologies, we have tutorial and some review articles, which will be resubmit it soon, hopefully. And I have my private lecture note on this topic with example Julia and Python.